Okay, so today's about shortest paths, more graphs. Graphs are fun. Okay, so a typical problem might be like this. I give you a directed graph and 2 points S and T. And, well, first you might convince yourself that you can get from S to T. But that's sort of what we did last time. And then today's question is, what is the fastest or shortest way to get from S to T? What does fastest or shortest mean? We're going to count, in this case, the number of edges that you have to traverse in getting from S to T. Okay? So I'll let you look at it for a bit, and then I'll ask. Okay. All right. What's the minimum number of edges you found to get from S to T? 7? Did anyone beat 6? Anyone beat 6? You take back 6? Oh, okay. Nobody even beat 7? Okay. Anyone beat 7?
This could be another trick where there's like a hidden little, like the cat.
No, the edges are just the blue edges, and there are no cats in this picture. Yeah.
What's the direction of the edge?
Oh, this comes up every year. I always forget that. Okay. All right, I'll put it that way. Every year this always comes up, and I always remind myself, let me draw an arrow for next year. And then I forget. All right, so 7, no one beat 7? Okay, what I'm going to do is I'm going to trace my pencil, and you can just tell me like which direction to go. All right? All right, so up and to the right or down and to the right?
Up.
Up and to the right? Up and to the right or down and to the right?
Right. Down.
Down? Like really up and to the right or to the right or, yeah, to the right-ish. Okay. Up or down and to the right?
Down.
Okay. Up and to the right or down and to the right? Down. Left or up? Okay. And then right. So 1, 2, 3, 4, 5, 6, 7. Okay, that's 7. Okay. Okay, I think that might be, but it's a little bit tricky to even like. Another question I might ask is, how do you know you have the right answer? Right now we have the right answer insofar as there's X many of you looking at it and no one spotted anything better. But the same could have been said for the cat maze last time, right? So it's not completely a certificate. Okay. So that's the problem we're looking at. That was like an unweighted version of the problem. We're just counting edges. But, wow, like the ground shook there. Okay. But we can give you edge lengths. Okay. So instead of just like 1 for each edge, it could be 1, 2, 3, 4. It can even be negative. We won't focus so much on that today. Next time we'll talk about negative edges. Nonetheless, so a walk is just any kind of walking through the graph, taking one edge at a time. Okay? And the length of a walk is just summing up the length of the edges on a walk. I should point out that walks are allowed to repeat. So a walk could kind of veer off like this or something. Or maybe it can also repeat edges. So maybe it goes like this. right? Where you're just kind of walking through that edge labeled 6 twice. Okay, then 6 will be counted twice in this sum. So this is with repetition, if it's repeating. Okay, so that's the length of a walk. Okay, and now I'm going to define the distance between two vertices. It's going to be, over all walks from S to T, technically the infimum over all possible lengths of walks from S to T. So that basically means the smallest length from S to T. But infimum is like a fancier word that says, okay, if there is no walk from S to T, we'll give it positive infinity. It really means the greatest lower bound. Okay, so if there is no walk from S to T, then that would like be an empty set. So infinity is actually smaller than any number in the set of attainable values. Or in some cases, the distances can be arbitrarily small. You know, for any finite length, I can find a walk that's even shorter in terms of sums of edges. So if it's arbitrarily negative, we'll call that negative infinity. Okay, so it's really smallest with some care around infinite values. Yeah?
Professor, what does the negative 8 length mean in the graph?
What does a negative length mean? Well, I don't know. What does a positive length mean? It is true that maybe we don't think about it as length anymore. But like, for example, we can have problems where, okay, it is true that you often think of a graph as like a map. You're physically moving around, right? But they could also be modeling like decisions. So each vertex is some state in like some big planning problem. And taking an edge, you know, you go from one state to another state, like you're playing a board game or something, and you get 5 points, or you lose 5 points, or something like that, right? So I always use maps as just an analogy because we're comfortable with, but then we'll have lots of, especially homework problems and stuff, that'll let you explore, like, oh, can I get a more liberal notion of going from point A to point B? It could be some state A to state B, right? Like you're programming a robot, it has an arm here, you want to get the arm to here or something, it has to go through some different states, etc. So, yeah.
So from this S to T, is it going to be negative infinity?
Well, okay, let's assume these are directed edges. So the length of this walk is just the sum of the edge lengths. So as drawn, I would just add up those numbers, and I would get, I think, a positive number.
Yes, but then what does arbitrary negative length? Is it negative 4 or negative 8?
So it's arbitrarily negative length ST walks. So that means like I could keep finding. So if you just the infimum is defined as the greatest lower bound. Okay, and so if you can always find for any fixed value, like you choose negative 100, and you say, oh, here's a walk where the sum is even smaller than negative 100. You pick another value, negative 200. You find something even smaller. That's what we define it to be negative infinity. It's smaller than, you can always find a smaller walk. Okay. All right. So even with negative values, which might seem unusual if you were thinking geometrically, you still have a triangle inequality. Okay, so the distance from, you have 2 points S and T, and there's some other point U. You know, if I can go from S to U and then from U to T, that gives me a way to go from S to T. So in that way, I can always, so now it kind of follows from definition, just from minimality, really from inf, that you have this kind of directed triangle inequality. Okay? It's actually, yeah. In fact, these distances are not necessarily a metric, but why?
Because D of S to T might be different from D of T to S.
Yeah, there's at least two reasons. One, it's not symmetric in a directed graph. And then two, also usually metrics don't have negative values. And usually 0 means it's the same point. So those are the ways in which it's not properly a metric. But you still have the triangle inequality, which is intuitive. Okay. All right. So there's this question we had, what's the shortest way to get from S to T? And like, okay, how, so we came up with some path, right? And my question to you is, our goal is to sort of turn this into an algorithm. So my question to you is, how can I, instead of like staring and searching, how can I really make something constructive, right? And really make an algorithm that always finds the shortest path? Another question we can ask is, how can we even set this up? Like, how do we even know that's the shortest path? How can we convince ourselves? Or what would we need to do to convince ourselves that some path we found is indeed the shortest path?
Explore all paths.
You can explore all paths, but if I take that verbatim, there's 2 to the n paths or something, right? There's exponentially many paths. So we don't want to enumerate all the paths. So we want to find out some compact certificate that's as good as saying we checked all the paths, but not literally checking all the paths. Yeah.
Can we try finding all attainable points from S to T and then do the same from T to S and get the common points?
Sure, but that's only going to tell you something about reachability. It won't tell you anything about
From
distances.
These points, the reachability, you can combine passes and get the minimum.
So you can assume that we already ran like depth first search from S, and we're only looking at things reachable from S because everything else is not going to be useful, right? So that's fine. That's sort of besides the central issue.
And then do the same from T to S, like reverse everything. And then
Well, that's not even going to help you, right? Because going from S to T has nothing to do with going from T to S. Yeah.
Every step we can make sure that we are taking it in positive.
Yeah, okay, so maybe here's like our first step, right? So we should at least be the shortest way to get there, because if there was somehow some faster way to get from S to this point, then we would be able to kind of shortcut it. Right? So if we can at least justify the first step, that's not bad. Okay. So do we feel good about the first vertex being like, for this vertex that I've circled, do we indeed find the shortest path from S to this point?
So in this, are we still assuming that's unweighted?
Yeah, still assuming it's unweighted. Okay, so I think the answer is yes, right? Because, in fact, both of these we know are all the vertices of length 1 away from S, because I think we're all comfortable with, length 1, you can only take one edge from S, and these are the only 2 vertices that are one edge from S, right? Okay, so good. We can identify that. Well, what would be the next step?
label other lists too.
Yeah, let's now try to identify all the vertices of length 2, right? And to do that, I would look at my vertices from length 1, at distance 1, and I feel good that I've done distance 1 correctly. And that lets me feel good about figuring out distance 2. Should be all the vertices that are one edge from distance 1, but aren't closer to S, so they don't have distance 0 or 1 already, right? Okay, so that's 2. And I would just do this, something like that, right? I don't know yet if we found the shortest path from S to T, but I feel very good about figuring out who's distance 1 and who's distance 2. I feel good about distance 2 insofar as I feel good about distance 1, right? And clearly you see the pattern. Now that we know distance 2, okay, maybe we can figure out distance 3. I always mess this up, so it's not as easy as it looks. So that's 3, that's 3, that's 3, and that's 3. Okay, hopefully I didn't mess up, right? But what are we doing, right? This is sort of like we're justifying, we're correct implicitly by what fancy word or process? No, neither of those. I had those in mind. Induction, right? I feel really good about length 1. That lets me proceed to length 2. Feel good about length 2. That lets me proceed to length 3. It'd be very hard for me to figure out what's length 5 without really figuring out the previous 4. I don't know how else to convince myself. Okay, so you can do something like this, and by building out these layers one at a time and being able to locally feel very good about this, then I can really feel like, okay, this point T is 7 steps away. Okay? But I don't think you can do it. Maybe there is a way, but I don't think you can do it without really identifying everyone who is closer first. All right, so that's our algorithm. Okay? It's not very complicated, but we just figure out the distances one layer at a time. Sometimes this is called breadth first search because you kind of build one layer and then you kind of expand. It doesn't matter. But you're just, okay, obviously S is the only vertex with distance 0 by definition. From there I can figure out distance 1. From there I can figure out distance 2. From there I can figure out distance 3. Okay? And yeah, that's it. Maybe you've all seen this before, so it's not so exciting, right? All right. So let's try to prove it's correct. Again, maybe it's very intuitive. So this is really more a matter of how do we articulate a proof of correctness. Okay, so here's a claim. So I'm kind of, notationally, I'm distinguishing two things. ds comma v refers to the true distance in the graph. Okay, and based on the pseudocode, this distance of v spelled out is the value assigned by the algorithm. Okay, so I want to argue that for every k, the value assigned is really equal to the set of vertices with the value assigned k is really equal to the vertices with distance k from S. Okay, and if we do that, that means we do everything correctly. So, okay, how might we prove this? Any ideas? We have some people speaking invisibly. I just need one person to say something. You get candy if you do. Or better yet, I won't give you candy if you do, and I'll force everyone else to have candy. I don't know which is worse.
Maybe we can consider two cases. So the algorithm says that as long as there is at least one vertex in this distance k, so we'll make two cases where we have one vertex and we have at least one and we don't have one.
Oh, okay, but then, sure. But now what would you do for, how would you go through the k's? Where would you start? Yeah. Yeah, let's just do a proof by induction. Okay. We've already kind of done that implicitly together, so it won't be so hard. So what might be a base case b? What's the easiest k? All right, we'll do 0. Okay, for ease of notation, I'm going to label one of these a sub k, the other one b sub k. All right, base case k is equal to 0, right? Okay. If I look at this a sub k, that is just S. S is the only vertex at actual distance 0, and the algorithm's that's the only vertex getting 0 in the code. All right, not a big deal. In the general case, rats. In the general case, why does this happen? In the general case, k is at least 0. Okay. And I think you just go through it sort of as you would expect to. So, okay, so I want to show that b sub k, which is a set of vertices labeled k, is in fact equal to a sub k, which is a set of vertices with true distance k. So I think we're just going to write down the definition. So the algorithm is going to set up b sub k to be the set of vertices that weren't in any of the previous layers, any of the B0, B1, B2, up to bk minus 1. But there's an edge from bk minus 1 to this vertex. Okay, so these are these vertices V, where there's an edge from U to V for some U in B sub k minus 1, the previous breadth first search layer. Okay. And by induction, I know that for all the previous k's, A sub k is equal to B sub k. Okay. And then that is our definition of A sub k. Okay, this is really not very exciting proof. But the vertices that are in fact at distance k will be the ones that have an edge from vertices of distance k minus 1. Okay, not too interesting. I think this is kind of already understood, but it's just writing it out. Okay, so I presented this sort of layered perspective, but I know you often associate breadth first search with a queue. Okay, so the way it's often presented, I don't know if it's a very good way, is you first set distance of S to be 0 and you put it into the queue. A queue means it's like a line. So things come out in the order they come in. Okay, so S goes in, S is the only vertex. And now you're going to take the first item from the queue, the first vertex, and then all of its neighbors that haven't been assigned a distance yet, they're going to have the distance equal to, if it's first S, 0 plus 1. But in general, if you take out a vertex of distance 10, it's going to be 10 plus 1 for all the new vertices. And then you insert it back into the queue. Okay? And to prove this thing works, you just observe kind of carefully that the vertices are being processed layer-wise, just like we did together. Okay? All right, no big deal. All right. Okay. Now let's look at the positively weighted situation. Next time we'll do negative weights. Okay? So the purple numbers indicate edge weights. 4, 3, and so forth. So, okay. I'll give you guys another chance to look. What is the shortest length from S to T? $15? Okay, okay, you could tell me how to get there. 12? Okay. All right, lead us the way to 12. Up and to the right, okay. Uh-oh, okay. All right, abort mission. No candy for you. Or no, actually, no, maybe we should punish you with candy. I don't know what to do with this. I can't, bring this whole thing back to the office. Okay. That's right. If you don't answer or you get a question wrong, you're now punished. I will throw candy at you. Okay? All right. So, okay. So here I am. Should I go up and to the right or down and to the right?
Up.
Okay. Now I'm here. Up and to the right or down and to the right?
Down.
Down. Okay. Should I go up and to the right or down and to the right?
Just go to T.
Okay, so that's 15. Can anyone do better? Okay. Same question though, how do we justify that you can't do better? So to build some intuition, at some level the only difference between now and before is that we've introduced these integer weights. How could I take this? Let's just say I had that unweighted algorithm at the black box. And how can I change the input or turn this into an unweighted instance?
Introduce nodes.
Okay, how? How would I introduce nodes? Okay, so we'll put 4 nodes. like this. Sorry, I'm going to get excited and carried away. If I put 4 nodes like this, like that. Sorry, I used the same color, so maybe that's bad. This 4 nodes? It should be 3, because otherwise it takes 5 hops to get from one to the other. Okay. So we can do something like this, right? So you can imagine splitting all the edges with nodes. And that will preserve exactly the distance information. Okay? So all our intuition just carries over. Nothing left to prove. And you could build out the layers, which I very carefully did this morning. But there might still be mistakes. I certainly found mistakes in last year's version. Okay. All right, so here's sort of an algorithm, right? You've given me an integer weighted graph. I split it up into edge weights, unit lengths with nodes, and I use breadth first search. It will be correct. But there's only one shortcoming. What is it?
Really slow.
What are you scared of?
It's gonna be really slow.
Why is it going to be slow?
What if you had like weights that were in the millions? You would suddenly have to go through like.
Yeah. So, okay. The only issue is the running time. The lengths might be really, really large. Okay, so here it's only 16, but if it was like a billion, gazillion, gazillion, the real problem is that you only need log of billion, gazillion, gazillion bits to write down billion, gazillion, gazillion. So if I describe a number to you in like 1 megabyte, which is a really big number because it's 2 to the million, this algorithm would never terminate. And you'd be like, why is it so slow on a 1 megabyte instance? Right? So, okay. Actually, I'm off by a factor of 8 because a byte has 8 bits. Okay, so how can we address this? I like the correctness from before, and it's just a matter of running time. Each real node, maybe?
Yeah, at each real node.
Okay, what would I store?
The distance to the node.
The distance to the node. So maybe what you're thinking is we can skip. Oh, sorry. Skip empty layers, right? So at some level, I can imagine taking our algorithm where I've split up the nodes, and like we know what it's going to do, right? We know that it's going to just be counting off until it gets to this vertex of edge 3. I can imagine sort of simulating it, right, without actually introducing the dots. What would breadth first search do? We feel good about breadth first search. What would it do? It would go to 3 first, right? That would be the first layer. So maybe we can figure out how to sort of skip the empty layers and retrace the exact same algorithm, but do it efficiently. So that's what we'll do. Okay. So I want to frame this as if it's just breadth first search made faster. Okay, so initially I'm setting the distance from S to S to be 0. That's the only one I know initially. And, okay. So what's the idea? So remember, breadth first search is always like building one layer at a time. So we're going to look at all the vertices U that have already been assigned a distance. So initially that's just S. Okay. And I want to figure out which one breadth first search would go to next. That would come from minimizing U plus the length from U to V over all the other vertices V I haven't visited yet. Right? If I had added one at a time, that's where I would, next interesting layer would occur. Okay, so all vertices U that have been assigned to distances, all edges leaving U, and then only looking at the endpoints V that haven't been assigned a distance yet. Right? 'Cause some of those edges might go backwards, so to speak. And then I'll assign it. All right, and return that. Distance labels. Okay, so I want to prove it's correct, a little more formally than just saying it's just doing breadth first search. Okay. And I think the key question here is, we could try to do something like induction like last time. Okay. But it's not clear what to do induction on, especially if it's not integer weights, it's real valued and stuff like that. Now we no longer require integer weights because we've kind of shed. We let integer weights sort of give us intuition, but now we're trying to do real weights. So if I wanted to set up a proof by induction, right? Before we did it on the length k, but now the length k isn't just like 1, 2, 3, 4 anymore. What else could I try to do induction on? Sorry? Path length. But okay, well, so I'm a little bit worried because sometimes doing induction on real values.
Number of hops I think you can use from.
Oh, number of hops. Okay. So number of hops. Okay. So here's okay, number of hops. So here's maybe one concern I have, maybe just like 1, 1, 1, and this is like 10 or something. So you should take the 3 ones, right? But if we do it by hops, then I'm going to be doing something, maybe even if I'm lucky, I'll do this vertex first in my argument. But my worry is that T is the next vertex in terms of hops. Right? T is only 1 hop away from S in some kind of proof. Yeah, so I'm trying to figure out how to kind of order and find some structure that lets me kind of convincingly establish that this algorithm is correct. Yeah?
Maybe the endpoints that have not yet been assembled. Because that set is the set of whose size increases as you progress through the algorithm.
Oh, okay. So I think implicitly what you're suggesting is very similar to what I had in mind. So the suggestion was, can we do it by induction on a number of vertices that have not yet been assigned a distance? So what's the base case?
We haven't assigned to anything.
So the base case is like n? And then okay, so it's only a little bit awkward because usually we prefer a base case to be 0. If I were to kind of flip it upside down, so the base case looks more like 0, and kind of rephrase, it feels like the opposite of what you're suggesting. So you're very close to what I had in mind. It's not the only way, of course. What can I do induction so that the base case looks more like 0 or 1 instead of n?
Just go with starting point.
Sorry?
Just go with starting point.
Sure. So let me be a little more precise. So there exists I guess there's 2 different ways to do it. So I can either number the vertices by true distance from S, which is similar to how many or I guess the way we set up here is, let's list the vertices in the order they're labeled. There's some concrete ordering given by the algorithm. Okay? And then let's argue that each one is correct. Because I think this is sort of in line with our intuition, right? Like we only feel good about the 10th distance that's labeled because we felt good about the previous 9. Right? Because we're kind of building up this thing. So let's just do an argument that sort of follows this intuition. Okay? So the claim is that for every index from 1, 2, 3, and onwards, that ith vertex we label is indeed the ith closest vertex from S, and it gets the right distance. Okay? This is actually a little bit stronger than what we strictly need. We really only need part B. But I think we'll see that we kind of need part A to justify part B. Okay. All right, so if I'm trying to prove this, what would be a base case? S, which is I is equal to. All right, so in the base case, I is 1. And here I think there's not much to say, right? So you can just read off the algorithm. It is setting the distance S to be 0 first, so V1 is equal to S, and that's what we expect. Okay. So the more interesting case is, what about the 10th vertex we label? Is that correct? Is it indeed the 10th closest vertex? And do we get the right distance for it? Okay. All right, so let's look at the general case then. So I is bigger than 1. And what do we have prepared for us? Okay, so this is just stating what the algorithm is doing. Okay, so it's the opposite endpoint, x, of the edge that sort of minimizes, v distance to Vj plus the length of that edge, where Vj is some other vertex that was already labeled. Okay, so that's one side. And now, how would I define the true closest, ith closest vertex, right? The actual 10th closest vertex. I know that whatever the shortest walk is from S to the 10th closest vertex, maybe the edge comes directly from S, or there's some walk there, but I know the previous vertex has to be closer to S. Okay? That's really all I know. And that enough is to tell me that the ith closest vertex is going to be kind of the opposite endpoint of an edge from one of the closer vertices, minimizing this sum, distance SVJ plus length E, right? And that'll give me the distance to X. Yeah.
Is it like whenever you add something to the queue, you sort it sort of?
So I think maybe I'm not expanding out enough as I should. So here I'm really assuming by induction that these two things are true, especially part A, for all the values j less than I. So down here, when I say j less than I really mean the I minus 1 closest vertices. Okay, so I know that the closest walk from S to the ith closest vertex, whatever that is, which might not be Vi, we want to show it's Vi. I know that it's coming directly from one of the closer vertices. So that, when I write such that j is less than I, that's sort of a compact, for lack of space, way to say it's coming from one of the closer vertices. It's a little awkward because I'm still trying to maintain some separation between what the algorithm does and what the truth is, except by induction, the algorithm and the truth coincide for all j less than I. Okay, now I want to show that the algorithm is correct for I. Okay, so what's the key point? The only real difference between these two definitions is distance Vj and ds Vj, where ds Vj is referring to the true distance, and distance Vj, maybe it's not the best notation, is referring to the label assigned by the algorithm. Okay? And here, they're the same by induction on that index I. Okay, I think it's coming out sounding not so great because I feel like this was layered into our discussion when revealing the algorithm. So hopefully this is actually more of just precisely stating what we'd already kind of come to understand together. Okay.
I'm still a little bit confused. Like, what's the induction assumption?
Yeah. So I want to argue by induction that I get all the vertices correct. And I have to do some ordering or some induction. Previously, it was on the distance labels. Now I'm ordering the vertices in the order that the algorithm labels them. Starting with the first vertex S, which I felt really good about. And so the simultaneous claim is that the 10th vertex I label is the 10th closest vertex, allowing for ties. And the distance I assign to the 10th closest vertex is the right distance. And the argument was really saying, if you got the previous 9 correct, then you're okay. Yeah. So I feel like this is actually over notation for roughly doing this. The real key thing is that the algorithm is really doing it by induction, and sort of only after establishing the first 9 are correct and the order you want can it justify that step 10 is correct. Okay. All right, so good. One thing kind of interesting is that, I don't know, somehow here the induction order doesn't come as directly from the problem as from the algorithm. Right? I kind of looked at what the algorithm is and used that to set up the induction argument. Okay. Well, forget the better part. All right, if we want to look at the running time of this algorithm, well, okay, let's see. How many loops are there over here? How many outer loops? Number of vertices. So, because you only assign each vertex once. Okay. And so naively, we'll do this a little bit quicker with some data structures in a moment. But naively, if I'm just doing step A, which is sort of compactly describing loops and stuff like this, naively, how long would it take to do step A, 2.A? This one. Sorry?
Is the number of edges that come from?
Well, yes, but how many choices of U? Yeah, so at least from what I can tell, it feels like you're looping over all possible choices of U and then looking at all the outgoing edges. So the total time for that would be M times N. Yeah, but I think what I would probably do is I would just loop over the edges and look at U and look at V and then see if distance was already done. So without too much effort, we could implement that in OM time. Okay, put that together, and what running time do we get? Okay, MN. Does anyone actually want a candy? No. Okay. All right, so now in the remaining time, we'll try to make this a little faster. Okay. But at least correctness is fully established. Okay. So at some level, right, when we naively kind of implemented this thing, one thing that might have seemed a little wasteful or excessive is that quantity, distance U plus length of UV, is like the same every time unless distance U gets updated by the previous iteration. Right? From one iteration to the next, most of the U's don't change. Only one U changed in the previous iteration. So we're just redoing the same computation again and again and again and again. Okay? So what we're just going to do is we're going to save this value and only update it when it is worth updating. So what we'll call it like tentative, right? So I wrote tentative of V is sort of the minimum of this quantity that we found so far. Among all U that has a label and edges UV. Okay, so I'm just giving it a name. And the key point is that each iteration will update some, but not all, of the tentative values. Okay? So we're just going to use memory to make this faster. Okay, so to this end, we're going to organize this information in what's called a heap or a priority queue. Okay. It has 3 operations. Maybe you've seen it before. So it's going to maintain keys and a value called a priority. Okay. So one operation is to insert a key with a priority. That's like a numerical value. We'll use that for tentative. The second is you can decrease. So here I'm describing a min heap. But you can take a key that's already in your heap in this bag, in this collection, which already has some priority, and you decrease it to a smaller one. And the third operation will remove the minimum. The key with a minimum priority from the structure. Okay. So the standard way to do this is to do it in log n time. And you guys probably already knew this. You guys remember how to set up an example of a min heap? How to implement one? Yeah, so it kind of looks like a binary tree. So each of these nodes will represent one key priority pair. Okay? And you keep it kind of full. So if you insert a new value, you'll put it into the next kind of open slot from a perspective of a full binary tree. Okay? And the rule is that you want to keep the values smaller going up. So it might be like, oh, if this has value 1, this has to be some value bigger, something like this. So it should get smaller. Those are the priorities I've written. It needs to get smaller on the way up. Okay? And if you insert something that's like new and it's out of order, like I put that 4 there, then you're just going to start bubbling this thing up. So I will swap the 4 with the 9. So the 4 goes up, the 9 comes down. The 4 is still smaller than the 5, and I'll bubble this up again. Something like this. And then, do you guys remember how to do remove min? Oops. I made a mess. Okay. So, if I want to remove the minimum value from this heap, then I know it's on top, right? So that's easy. The question is, what am I going to replace it with? Okay, you could do the smallest one, but actually it gets a little bit tricky because if it's like this or something, you would replace it with this one, right? And then something else would have to get replaced like this. And what would happen afterwards is that you'd have something that looks like this, the structure. It would become uneven. Okay? And the only reason the algorithm has log n time, I'm probably talking about this too long, is because it's a full binary tree. So what you actually do is you kind of take that last slot. This might be a very big number. You put it up in the top to replace it, and then you bubble down. But this will keep the shape correct, and then you bubble down to keep this hierarchical thing. Everything's log n because the height's log n. Okay, so you can do that. Okay, and so we can maintain a priority queue where the vertices have priority based on their tentative distance. Okay, which is infinity for everyone except for S to begin with. And then I keep pulling out the minimum vertex based on tentative distance, making it official. That's the 10th closest, 11th closest. And then updating the outgoing edges. Okay. All right. So, okay. So if that was the case, it would start getting faster, because this would take log n time and stuff. So, and then this you only do once per edge. Okay? And it takes log n time to decrease someone's priority. So you put that all the way through, and you're going to get m plus n log n, or really m log n. Okay? Sorry, I ran a little bit over. Now, what's amazing is that there's a more elaborate data structure that I won't describe the implementation of. We might do it later in the class, but it requires something called amortized analysis. And what it lets you do is this operation it can do in constant time on average. Okay, that means each individual one might be longer, but if you do 100 of them, it's going to take big O of 100 time. Okay. So on average, it's always in 100, and we'll elaborate on this point a little bit more later when we talk about amortized towards the end. Sorry about that. But if you plug all that in, okay, we have n iterations out here. It takes log n time to remove a vertex, but each vertex only gets removed once. And when I call decrease min, it now takes constant time. Okay, you drop that in, and you now get m plus n log n. Okay, all right, end there. Thanks. So last time we talked about shortest path, trying to get from point A to point B as fast as possible, and so I thought it would be good to, since you're gonna have plenty of homework about it, it would be good to do an exercise together for the first half, and in the second half we'll start the next topic. So I have this problem that's also like some kind of shortest A to B kind of problem. So I'm going to give you a directed graph, and the edges will have positive edge lengths on them, or non-negative. And your goal is to get from point A to point B as fast as possible, except you can only use an even number of edges. Okay, so I just kind of took the standard problem and threw in a little bit of a bell and whistle. Okay, so maybe to make sure we're on the same page, we can try to solve this problem. This particular instance, I'll give you a chance to look at it. All right, so what's the best anyone ever gotten? So what was your shortest length of any even number of edges from S to T? $16? Anyone else get 16? Anyone beat 16? Okay, how do I get 16? I'll start here and I'll ask you to direct me. So should I go up and to the right or down and to the right? Oh, you no longer have 16? Okay. 17? Okay. All right. So should I go up and sorry? I thought about bringing like I am going to bring back the candy. But I felt like some of you actually didn't want to answer questions. So I have to wait until your guard is down. I need to earn your trust back so I can break it again. That's how this abusive relationship works. What? Okay, not so fast. 15? Okay, just ignore that corner. Okay, they're too ambitious. Okay, so you said three. Okay, so I should go down. Okay, right, up, right. Oh, right. 11, 17. Did anyone get better? This one it's really hard to tell if it's the right answer or not. Right? So okay. So that's the problem, and we can all have fun and talk to each other for the next 5 minutes or something. So your goal is to get an algorithm that will find the length of the shortest walk from point A to point B, given a directed graph. Okay, so I'll let you guys work with each other, and highly encourage you to have some paper out or something. If you don't write it down, you won't really know. Yeah. Yeah, so last class for unweighted graphs, we did breadth first search in m plus n, and we did Dijkstra's algorithm for wedge weights in m plus n log n. Please talk to each other and stuff so it looks like it's not a prison. I do encourage you to try to write down or type it down a little bit because always people think they have an algorithm but haven't really nailed down what they mean by it. Like often people are like, "Oh yeah, of course you can do this," but sometimes it's harder to get it down and really explain what you're doing. Do you all want to start discussing or you want to write a little more? Sorry?
Sure, the answer.
Just what? Oh, you just want to go. Okay, you want to discuss. Okay, so what did you come up with? Who felt like they had a good algorithm that they want to share with the class? Yeah.
So I was storing the minimum distance to each node for its even and odd path. So that way we can then, once we get that through like Dijkstra's algorithm going through every single node, then at t you can find the minimum distance from node previous to t based on its odd length.
Okay, so intuitively you want to figure out for each node the shortest way to get there via an even or odd number of vertices. And you said, okay, then I can do something with Dijkstra. So now imagine you're trying to actually write this down, right? So okay, that much I think we're on the same page. Now, how would I describe and start writing an algorithm? Sure, a recursive spec, but is the intent, for example, to try to, for example, should I take this Dijkstra's algorithm and copy and paste it and start trying to adjust it? Is that what most people tried? Okay, let me do that. I think that's the copy button. Okay, so you have in mind sort of a modified Dijkstra's algorithm. Okay, so here's Dijkstra's to get us started, and maybe I can just cross things out. It would be a little messy. We'll try our best to change it or something. So tell me what I should change. Yeah.
When we're like having this tentative test like for a vertex, we can have like a parity
Yeah, okay, so tell me again what I should do.
like tentative s comma row
Okay.
that would be
So maybe we don't even have to, we have higher level languages, so we can call it even or odd. Okay. So okay, you want to add kind of like v comma even or v comma odd. And I guess s would have to be, this would be probably s comma even because 0 edges is s. And actually you have to be a little careful because actually you should probably set tentative s odd to be infinity to start. Okay, so of course it's gonna be a little messy, so bear with me. Okay. Uh, okay, so something like this. Okay, so I've changed the first two lines. I also said the priority is decreasing in tentative v comma x, where x is either even or odd. Okay. All right, so let's keep going. Maybe 3 while q is not empty. We don't have to change that. Remove the vertex. So I guess it'll be the kind of, I don't know if we'll call it vertex. I guess v, I'll write f for flag or something. Oh no, maybe I'll write p for parity of minimum tentative v comma p, I guess. So p will be either even or odd. So maybe up here, I'll try to make that consistent. So I'll use p because it stands for parity. Okay. And then I guess you'll set distance v comma p to be tentative v comma p, right? And then now for each outgoing edge from v to w, I guess I'll let q be not p. I don't know if that makes sense. So even goes to odd and odd goes to even. And and you would want to set like WQ to be the minimum of WQ, or V comma P plus L VW, something like this, and then decrease W comma Q priority, something like this. Okay, so is that what a lot of people were doing? Okay, here's the next step. How do we prove this thing works? You have a new algorithm, you have to have a proof, right? So to prove this correctly, we'd kind of have to go through and retrace and roughly redo the same proof that we did for Dijkstra's. It's a little bit dull, but a new algorithm requires a new proof. Okay, so from your perspective, you should be thinking, I don't want to write a long proof. Okay, but in real life, what you're kind of saying is, I've created something new, and I need to explain and convince my coworkers or my teammates that this thing is correct, right? Even if it doesn't have a rubric with certain points like we give on the homework, you still need to justify what you did when you do something new, right? So, okay, so some of what's going on, right? With this kind of V comma P, we just replace all the V's with V comma P, right? And that's, I think, what we're all intuitively thinking, okay? So suppose I'm very lazy and I didn't want to invent a new algorithm, but I wanted to do something similar. So here we've actually changed Dijkstra's to, like, I don't know, parity Dijkstra's algorithm, right? Suppose I wanted to use Dijkstra's algorithm as a black box. I don't actually want to change the algorithm because I don't want to reprove that the algorithm works just because I changed some stuff. Okay. How could I do something similar? Maybe essentially the same, but without changing the algorithm. Well, at the very least, that'll make things a little bit slower. So this running time also mentioned is relative. Okay, what's the running time of this algorithm? Maybe it's worth going over this. So before Dijkstra was m plus n log n, where n refers to the number of vertices. And why do we feel like that's the same here? So I guess each vertex I'm only looking at twice now, once for each parity, each edge, sort of once for each particular parity, at some level at high ID. Okay, but let me get back to this question. We have this great black box algorithm, Dijkstra's algorithm, right? We spent quite some time last time carefully proving this thing works. I feel very good about what Dijkstra's algorithm does. And I kind of feel okay about this partly because I know the answer. But it's already a little bit more complicated than what we're doing, right? And if I give you a more complicated problem, it might be even messier. So this will maybe be better motivated on the homework when I'm going to, replace the even part with more and more complicated things. So how can I roughly do this logic by using Dijkstra's algorithm as a black box? Yeah.
I don't know if this is right, but like we're given the distance labels from use that information to like determine what.
So you have a subroutine called Dijkstra. You give it a graph.
Yeah.
But the distances it will return doesn't think about parity, right? So you get these distances from point A to point B, but it takes into consideration nothing to do with parity. So that's not exactly what you want. Yeah, but it's not going to be even, and then what? Dijkstra only returns one number, and the next might also be odd. Yeah.
Can we like store the odd part and even one separate? Like if you update the
How do I do that using Dijkstra as a black box? Dijkstra takes something as input, yeah. Okay, so you could do this. So you could sort of like, oh, let me replace every 2 consecutive edges with the one combining it. Like this edge will become an edge of length 8. It's 2 hops of length 4. But one thing you have to be careful about is that if I drew all these green lines, the number of edges is going to go up by a lot, right? Because all these pairs of edges. So, and that will hurt your running time. No, imagine I have a vertex of degree n. If I have a very high degree vertex, right, with lots of edges coming in and lots of edges going out, the number of pairs I can make is the product. So you can go from n to n squared rapidly. Yeah.
So first call Dijkstra on the weighted graph, and then maybe call Dijkstra on the weight force. So it's like Dijkstra of n, w, and then another Dijkstra on n and e, assuming all weights are 1, so that we just give the pop distance. And then based on the pop distance, like even or odd, that's how we can decide some.
That's not going to work. Well, why would it work? I don't know. It tells you the distance is 10, and you can also get there with 4 different edges. What does that tell you? No, for example, the minimum number of hops may be a completely different path than the minimum length. Well, okay, so you have a black box Dijkstra. You can't change the algorithm. You're calling Dijkstra on X, and you can't change Dijkstra. So you can try to change X.
Is it possible, like, once you get the return from Dijkstra, you can remove one of the like edges of the path and call Dijkstra again, like for each edge on the path, remove it and call Dijkstra again, and hope it finds.
As soon as you say hope, which happens in half the answers, almost automatically no, right? Like the answer is going to be very clear why it works. That's one of our goals, is to not just solve problems, but solve them very clearly. Okay, so, okay, here's a trick. So what? I have some graph, right? And it has these edges, something like this. I'll draw another edge like that, or something. Okay, so I have a graph, right? And I want to encode at some level this extra state of whether I, yeah. Yeah, so vertices really represent states. Okay? And an arrow is some transition from one state to another. And implicit in our code was, oh, I've gotten here in an even number of steps, and I'm going there now in an odd number of steps. And I'm really going from the state, like v comma even, to another state w comma odd, taking that edge, right? So how do you encode that? So I'm going to take this graph, okay, which has, this is an abstract picture, and I'm going to make 2 copies of the same vertex set. And I'm going to call this the even copy and this the odd copy, okay, of all the vertices. So let me erase these edges. Okay. So I've made 2 copies of every vertex. One is kind of like v comma even, the other one is like v comma odd. Right? And now for each of these edges, like this one that's going like this, so this should correspond to one edge like that and one edge like that. Okay, so I'm going from v comma odd to w comma even, right? And same here, like this and like this. Okay, so I just duplicate the graph like pancake layers, and I drew the edges accordingly, right? And now I just have another directed graph, and I'm trying to get from S even, which is some vertex, to T even. And it's going to hop around, hop around, hop around, but it has to go down and up to get back from S even to T even, right? So you're guaranteed an even number of edges. And I just run Dijkstra. Yeah.
Are you thinking like D even and D odd is like two distinct?
Yeah. So down here, there will also be S odd and T odd, or T comma odd. Yeah.
Can you draw like a really simple graph?
So yeah, this was supposed to be my simple. So up here there was S. Here's T. And maybe I'll number these A, B, C, and D. Those are 4 vertices. So this is a very uninteresting graph. And I've made 2 copies of every vertex. B odd, A odd, C odd, D odd. As usual, apologize for handwriting. And I've made 2 copies of every vertices, and I've connected the edges from like the odd version to the even endpoint. Okay.
What does A even stand for?
I've made 2 new vertices. So I took the original graph and I'm making a brand new auxiliary graph. I'm calling, for each vertex I make 2 copies. I call one of them A odd and I call the other one A even. Okay. And what those names are doing is remembering whether I've taken an even or odd number of edges up to that point. Okay. And now each edge sort of appears twice because each time it's flipping the parity. So if I want to go from S even to T even, and there's some, real path in the graph, now it's going to like be zigzagging back and forth where it goes there and 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 back to eventually T even. Okay. So I've made 2 copies of every edge. So it's like the same thing going on, same thing going up. Okay. So, every even length path up there maps to a path between 2 even vertices, 2 kind of vertices labeled even in the auxiliary graph. And vice versa. If I can go from S even to T even, then I can look at the underlying edge and I get an even length path in the graph. Okay? So that tells you, okay, the shortest path from S even to T even in the auxiliary graph is the shortest even length path in the original graph. Once I establish this mapping, these paths here are these paths with that property there. Those paths with that property there are just paths down here. Dijkstra guarantees the shortest path, but because it's going from S even to T even, I get the evenness in the original graph. Okay? But now I don't have to reprove anything. I just reuse what we did last class as a theorem. I know that Dijkstra, given a graph, finds the length of the shortest path from A to B. And A to B in that graph, the duplicated graph, will give me an even length path in the original graph. Yeah.
So what does it mean if you go from A even to A odd? Is that possible? That means that.
Yeah, so we don't draw that edge. You can't go from A. So, okay, I only drew pictures, but yeah, explicitly, you would have, some graph G equals VE, and you're going to make a new graph. I'll call it G bar is equal to V bar E bar, where V bar is going to be 2 sets of the same vertices, which I'll call V odd and V even. Okay. And E bar is going to be the set of all edges of the form. So you would want to actually write out explicitly how to build it. It's not so hard to build on a computer because you just loop through and build the thing, right? So it's going to have all edges of the form U odd to V even, where UV was an edge in E, as well as the other one. All edges of the form U even V odd for UV is an original edge in E. And you also have to be careful about edge lengths, right? Because Dijkstra is expecting a weighted graph. So you would also want to explicitly define your edge lengths. So you would define like L, for an arc that looks like it's going from U odd to V even is going to be the length in the original graph from U to V. And then same for the other one. U even V odd is equal to LUV. Okay, so there's none of those A odd to A even edges. I just don't include them because I don't want that to happen. So I get to make the graph. Yeah. Oh, you had a question, but you took it back. Yeah. Sorry? Yeah, so I am trying to, in our algorithm, each time we took an edge, we also flipped the parity. The one we did together first, right? Which people felt like they intuitively understood. If I was at like V comma odd and I took an edge to W, I would go to W even. And so that's exactly what we're doing. So if I have an edge U to V in the original graph, that should take me from U odd to V even. Because it's taking me from I've reached U in an odd number of steps to I've reached V in an even number of steps. And you have to do the other one, right? Because you could also go from U even to V odd. So I just need to do, going from odd to even and from even to odd to encode things. Those are the two copies for an arc. Yeah. Well, for every edge in E, I make this graph. So I just loop through the edges in the original graph. Yeah. Yeah, yes. You could have also looked from S odd to T odd, yeah.
Yeah. How about if that's the case? Like, imagine if A was a source.
Uh-huh.
So A ought to be even doesn't make any sense now.
Well, that would give you an odd number of edges, right?
Yeah, no, but you go to B even, but you only make one out, but A is a source.
Yeah, so you wouldn't do that. Yeah.
No, I'm like saying like there is a possibility that you're saying you would never call the algorithm like that.
So after you describe your construction, you would need to do a little bit of an if and only if, right? And then you clearly establish, okay, uh, if you establish that any path from S even to T even in this graph corresponds to a path from S to T with an even number of edges and the same length in that graph, and vice versa, you observe that any path from S to T with an even number of edges maps to an edge, a path from S even to T even in this graph. Because Dijkstra just promises, I will get you the length of the shortest path between S even and T even. So then you need to do a little bit, and if and only if, check both directions to show that, oh, that will give you the even, the minimum even length path from S to T. And then you do that, and then you're convinced and you've fully established it. Yeah, so you do need to justify and double check, and do both directions, if and only if. It's not too big, it's not too small kind of thing. Yeah.
Professor, like for a graph, it's just 2 4 points. Could you please do how you separate them into even and odd?
For every vertex, I make two copies. One called S even, one called S odd.
Okay, so it's just called S even and S odd.
Yes. So I just make it. And it's convenient because it encodes all of the bells and whistles from the problem directly into the graph. So I've taught Dijkstra how to solve my more complicated problem that Dijkstra wasn't ostensibly initially made to do. Yeah. Yeah, I think one of the first problems on the homework is, what if it's a multiple of 3? And I think I give more, like, any number of edges that's of the form like 2x plus 5y. Yeah, you can play this game, and then there's more. I give the edges colors, and an American walk is one that goes red, white, blue, red, white, blue, red, white, blue, to figure out how to do that. Yeah, so you'll get plenty of practice. Yeah. Yeah. Yeah, it's or sometimes called a bipartite graph, right? There's two parts and the edges only go from one part to the other.
Yeah.
Yeah.
So like to maybe another way to deal with
But yeah, but at the end of the day, I'm just trying to solve the problem in the top left corner, right? You're given some graph and you want to find the even length thing. And then yeah, the construction naturally begets a nicer graph, but yeah, but we don't really leverage. Yeah.
So this is a I've heard it mentioned.
Well, we're just doing a path problem, right? For this case, we want to solve a path problem. Yeah. That's just more of a, yeah, matching is just a different problem. That we'll do later. But the theme is sometimes you don't, even though it's an algorithms class, you don't change the algorithm. Okay, you change the input. Okay, and then you can get for free all the things that we carefully, fully proved and established. If you make a new algorithm, then you have to actually prove it and reanalyze it. Okay. Yeah, so I always say that roughly most problems can be solved in one of two ways in this class. One is to figure out how to turn it into subproblems. So anything by induction, if you get that sentence right and you've identified the subproblem and how to peel it away, you're basically done. And the other is by changing the input to an existing algorithm. And many of our problems can be put in one of these two camps. But they're both different styles of thinking. They're both, I think, counterintuitive, unnatural ways of thinking, but very effective. Yeah. Yeah. Oh, so we should do this, right? So yeah, a full solution would then have to say, what's the running time of this algorithm? So Dijkstra runs in the number of edges plus number of vertices log number of vertices, which has changed, right? We have a new graph. So we need to figure out how many edges there are in the auxiliary graph in terms of the original input. Same ways, right? So let's do that. So I want to calculate, so how many vertices are in the new graph? So size of V bar, right? That's the number of vertices in our new graph. How many vertices are there? 2 times the previous. 2 times the previous, or if I'm using n for the number of vertices originally. And now what about the edges? Same. So that's what we plug into Dijkstra's running time. So you get, I'll write it out, but 2n log 2n, sorry, it's a little hard to see, but of course the 2 doesn't matter in a big O. So you end up getting m plus n log n. Okay. So you lose nothing on the running time. It's much easier to see why this is correct. Okay. And if you really imagine what Dijkstra is doing on this algorithm, it's not really so different than us trying to hack into and change Dijkstra's algorithm directly. You can actually imagine it ultimately doing steps like this. But this way, it's very easy to analyze, understand why it's correct. You don't have to convince your teammates that your changes are messing something up, right? Insofar as you and your teammate understand what Dijkstra's algorithm does and does not do. Okay. Yeah. So this will be a theme in the class, being able to relate these problems. Okay. That was fun. Any questions? Any more questions?